Cindy, you can go ahead.
So hello, this is our modern physics class's final project. So today we'll be examining two theories, which is compositeness and chameleon particles. But first we're going through an overview of each theory, then we're presenting our accelerator and the two competing tracking detectors. So first I'll talk about compositeness theories. So there's a lot of them out there, and they essentially all say that the current elementary particles as defined by the standard model, they could actually be made up of smaller particles that would have a substructure. There are many of these models, such as the Rishon model, which predicts that the quarks are made out of smaller constituents with balancing charges. Also, the composite Higgs model. Today we'll be focusing mostly on quark and lepton models because that is what our accelerator and tracking detectors are designed to test. So essentially, an elementary particle is a particle that cannot be broken down into any further smaller constituents. So thus, you would expect it to be point-like. However, if a particle is in fact composite, then it is made up of smaller particles and it would have some size. And you should also be able to see interactions between the smaller constituent particles. Now, this is normally not very noticeable at lower energy levels. However, above the energy scale lambda, you should start seeing deviations from the standard model due to these new interactions. However, currently, since we don't have very conclusive evidence of compositeness, this suggests that energy scale lambda is actually very high. So when testing for compositeness, you would want to create interactions with as much energy as possible to look for possible effects of compositeness.
Just go ahead and move to the next.
Okay.
Just click to move to the next slide.
Oh, okay.
Just move to the next person. Go.
Okay, so basically, assuming that the energy needed to observe a composite interaction is reached, the effects should show up in the dijet. That is wrong. Not as an increased number of observed events, but as an increase in the. What was it? Okay, so it's the number of dijet events with a given invariant mass, and the larger the mass, the more pronounced the effect. So basically, if the number of digets observed, or if the number of digets with a given invariant mass is observed, then or is significantly greater than the standard model prediction, then it's an indication that compositeness was present. I have two graphs, and let me remind myself what they were. The first one is a dijet spectra generated in Pythia or Pythia with the quark compositeness turned on at lambda is 3 TeV, and so that's the top figure, by the way. The bottom one is a comparison for the D0 data with several different theoretical predictions given at different lambda values, so at 1.5, 2, 2.5, and 3 TeV. And then there's error bars which show statistical errors and whatnot.
What's the difference between the left and the right ones on the top?
That is. Honestly, I don't remember. I think it was something to do with just a version where one of them was a different version. I'm not sure. The actual, there was nothing on that in the paper that I quoted from. There's nothing on that, so I was confused too. But I mentioned something about switching versions in Pythia.
Okay. Okay.
Next slide.
Okay, so I'm going to talk about compositeness and bad lepton events. So in hadron-hadron collisions at high energies, massive pairs of leptons form through the Drell-Yan process, where quarks and antiquarks annihilate to form dileptons. And they're well separated from jets of hadrons and other particles that are formed after a collision. So it makes the process experimentally distinctive, and it makes the process of background discrimination a lot easier. So if preons exist, their constituents must interact. So at energies well below lambda, which is the compositeness energy scale, we can model the binding interaction through a 4 fermion contact interaction, and because of that, we can increase the rate of dileptons at a given invariant mass. So if these contact interactions are observed, there would be a significant deviation from the standard model's prediction on the dilepton invariant mass spectrum. But if there are no deviations from the standard model, you can increase the lower limit on that.
that then the theory
That's-
That's the compositeness section.
That's the compositeness. Okay, so you can look. So what are you looking for? You got dijet band spectrum that you're going to look at, and
Dilepton invariant.
dileptons.
Yeah.
So 2 jets or 2 leptons. Is the theory experimental? Is that the theory signature you're looking at? Okay.
Okay.
Sounds
Next
good.
slide.
Sounds good. Yeah.
Good.
Good.
Chameleons.
Alright, so our group, as opposed to compositeness, chose to focus on research on chameleon fields and chameleon particles. Now, cosmic inflation indicates that there's a correlation between the distance between cosmic bodies and the rate at which that distance increases. That is, the farther away cosmic bodies like planets or our most significant galaxies are, the faster the distance between them increases. Now, a logical cause for this kind of odd phenomena would be some kind of force which is sensitive to matter density, which is, it's stronger where matter density is low or where there's less matter, and much weaker where matter density is much higher, like planets or galaxies. It's actually really important that it functions in this manner, because such a force would cause pretty noticeable violations to Einstein's equivalence principle. And here on Earth, where matter density is high, and therefore this force would supposedly be much weaker, Einstein's equivalence principle supposedly holds, as far as we can tell. Quintessence is the name given to this theoretical new force. Yeah, quintessence that is its name. Okay, so this theoretical fifth force is mediated through the chameleon field by chameleon particles. These chameleon particles allow the fifth force to function in this matter density sensitive manner, which it is kind of supposed to do, because these chameleon particles grow in mass in areas with high matter density, but as they grow in mass, their interactions become much, much weaker. Whereas in areas with very low matter density, these particles shrink in mass, or shrink in matter or mass, but their interactions become much, much stronger. And that's a chameleon.
Change the next slide.
Are there any questions?
Wait.
Let's see the next. Yeah, the next.
Okay,
You stay
so
up there,
how do we
stay up
detect
there.
these chameleon particles? So, as Matt said, in areas of high matter density like Earth, the force is weaker, so they're hard to detect. But since that they must still interact with matter, then, or since that they change the dependence of matter, they must interact with matter. So we can use that to see how they might affect things. Previous research has shown that they don't affect the decay rate of the Z boson, and they don't have any noticeable effects on regular gauge boson fermion interactions. But the one type of interaction that they would have a significant noticeable effect on would be Higgs production. Specifically, the chameleon would allow these 4 different couplings between the gauge bosons like W and Z and the Higgs boson, which would increase the rate of Higgs production slightly. And so, because of this, we want to measure Higgs production very precisely so we can see if there's any deviation. We do know, also due to previous research, that this correction in Higgs production due to chameleons would not be noticeable at like around 10 TeV or below, which is why the LHC wouldn't be the best for this. But since our new accelerator has higher energies, as you'll see for the accelerator group, we believe that we can use it to detect chameleons in this way.
Okay. Is that it for this
Yeah.
theory section?
Yes.
Okay. So this sounds like it interacts with matter the opposite way that gravity interacts with matter. Is that right? Okay.
Yes.
And you are, what is your, so you would notice an effect only in the Higgs
Yeah.
production?
Yeah.
So what's your experimental signature? What are you are you just like going to add up all of the different Higgs decays and look at how that's different from the?
I believe that would be what we would have to do because it's really the only thing that has been shown to be affected by
It's just the production.
just the
of
production of
Higgs.
the Higgs because
Okay, and okay, so the Higgs production is the only thing that it's going to affect, and then you're saying that if you're below 10
Right.
GeV, you won't see this in the Higgs production.
Right, you won't because if chameleons exist, that these interactions would still happen, but there would be to such little effect that it would be essentially unobservable, which is why we need to go higher.
And they don't interact via weak or strong or EM.
Yeah, we don't believe so.
I'm not super familiar with this theory, so it's very weird.
It,
Okay. Okay, alright, I think I got it.
Accelerator.
Alright, so this is our accelerator. We designed one accelerator complex to test for both compositeness and chameleons, and we have 2 collision points, so we can install 2 detectors. It is a mu-1 anti-mu-1 collider with a maximum center of mass energy of 70.65 TeV. So we start with a proton source, and then we go through 4 acceleration stages. And our stage T-4 is a linear accelerator with 884 RF cavities to reach a energy of about 883 MeV. Then our stage T-3 is a synchrotron with standard magnets and a radius of 59 meters to reach a maximum energy of about 17.7 GeV. Our stage T-2 is a synchrotron with standard magnets and a radius of 1,180 meters to reach an energy of about 354 GeV. And then our final T-1 acceleration stage is another synchrotron with 90 superconducting magnets, a radius of 2,622 meters, and a maximum energy of 7,079.4 GeV. And because our muon and anti-muon sources produce particles at about 25% of the input energy, in our T-1 acceleration stage, we raise the protons to about 20% of our maximum beam energy, so we can produce them at a high enough energy to put them directly into the collider. And our collider is a synchrotron with 8.9 T superconducting magnets, about 27 GeV of RF, and a radius of 13,232 meters, with a maximum beam energy of 35.3 TeV, which is high enough to potentially detect effects for both chameleons and compositeness. And because we are using muons, which decay rapidly, we have 14 of our T-1 acceleration stage to act as storage rings for the protons, so we can use a slip stacking technique to increase luminosity.
So for the cost section, we were given a budget of $15 billion, and we got very close to that. We came within $15,000. So to do this, we had to do a lot of strategies to keep costs down. So we decided to build most of our accelerator on Fermilab's campus, and we don't know the exact proportions for Fermilab's campus, so we took the maximum area and assumed it was a square, which gave us a radius of the T1 accelerators that we had in the previous slide. And so for everything T1 and below, we built that 10 meters under on Fermilab's campus because we didn't have to worry about residential housing, so we didn't have to worry about any legal things that might have to come into that. And so we also stacked the 14 T1 accelerators within 3 tunnels because that was the thing we were told we could do. This helped save a lot of money on cost for tunnel digging, which was very useful. Because we couldn't fit our T0 accelerator on Fermilab's campus because it's huge, and there are no magnets strong enough to do that, we had to dig down 100 meters using 4 tunnels, which only looked like 2 tunnels on that. So once we got down, we had the muon and the anti-muon sources, and then we pushed them all into one the T0 accelerator, which was dug at 100 meters because it went under residential housing. And that basically sums up everything we had to do for cost.
So you're gonna dig 3 brand new tunnels? You're gonna dig 3 brand new tunnels?
Well, the assumption was there was nothing there.
Okay.
Like we found an exact copy of Fermilab's campus somewhere else. Yeah, a square version of Fermilab. But yes, that was the idea.
Okay.
So with our accelerator, luminosity, and more practically speaking, integrated luminosity is an important measurement of the performance of our particle accelerator and how much data can we collect. And we calculated luminosity using 3 main factors: the collision frequency,
and the number of particles per bunch, and the beam widths. The frequency and the beam widths were two set numbers. We really couldn't play around with those. For beam width, it was 1 millimeters for the muons, and frequency was just based on how it was Dr. Long gave us that number. But the number of particles was what was changing, and especially because we used muons. So muons had a 1% production rate. So as Katie said, we produced our muons from a proton beams, and so 1 muon was produced for 100 proton beams, which really declined our luminosity. So to raise it back up, we used a technique called slip stacking, and I kind of gave a drawing here. So we would use 7 proton beams, and we would send it to a muon source. The other 7 beams would go to our anti-muon source, and from there we would each have them hit their source, and from there that would almost act as like a 7 times multiplier to the bunch sizes of our muon beams and our anti-muon beams. So that didn't make up for the loss from production rate, but it kind of helped raise our luminosity. But since we were using muons and anti-muons, those are unstable particles, so we had to account for the decay as they went through that final accelerator, that final synchrotron. So to limit that decay, we made sure those muons had a high energy, because the higher their energy is, the higher their gamma factor is, which would lower the amount of decay. Also, to limit the amount of time they went through the synchrotron, we had multiple RF cavities, as Katie said. It was like 27 GeV per turn. So because it was gaining a lot of energy per turn, it required less time to reach that max energy of 35 TeV around there. But we also had to account for synchrotron radiation, since we're using a circular accelerator. Each time it turns, it'll lose a bit of that energy, requiring our muons and anti-muons to accelerate for more time because they're losing energy as they gain energy. So it's kind of like you have to take more time to get that max energy. We didn't account for neutrino radiation simply because the neutrino flux was directed in multiple angular momentum. So finally, once our neutrinos reached their max energy, we plugged it into this formula, and our final luminosity is 1.4 times 10 to the 30th. I know which is lower than other LHC luminosities, but I believe they use protons and muons decay, so it's yeah.
Okay, go back to the first accelerator slide. Okay. So when you say in the collider and you say the max energy, are you saying max energy per beam is 35 TeV?
Maximum
Yeah.
beam.
Okay, okay. And you're gonna make, how do you, I might have missed it, but you said you're gonna send these particles you're gonna send protons, 7 of them, through to targets, and you're gonna produce the muons and anti-muons from there, and at that stage where they're produced, they're at 17 TeV?
They're at 1.7 TeV when they're
Oh,
produced.
1.7 TeV.
Yeah,
How do they get up to the 35?
In the final.
They're produced at 1.7 TeV, and at that energy, they are placed into the collider, and they accelerate to 35 TeV in the collider.
So that's where all the muon decay is happening in that final collider while we're
Okay.
accelerating.
Okay. Okay.
A lot of okays.
Well, because I assume you guys researched muon colliders when you started this. Slightly, yeah, and it's very hard. 1 Tesla magnets, yeah, yeah, it's quite difficult.
And we have the muons and anti-muons doing
How are
We
this.
you-
didn't use 1 Tesla.
For the collider, we have 8.9 Tesla magnets.
Sorry, that's also quite okay. What about so I also don't know a heck of a lot about muon colliders, other than they're very, very difficult, and people are always worried about muon cooling. Did you guys research this at all?
We didn't hear anything on muon cooling now.
So that might be something to check out, but that's like one of the problems with the colliders is they're trying to solve. I think it has to do with making sure that when you produce muons, right, going through the target, it's hard to get the exact momentum that you're interested in, right? So you're interested in a very specific momentum, I assume, right? Because otherwise your bunch train spreads out and then you can't keep things together, or do you want them to spread out? You want to pick very specific muons.
Yeah.
So you have to do like this muon cooling kind of thing to make sure that you get them all close to the same momentum as possible.
Right, and I'm not completely sure about that, but I think that might be a factor in why there is only a 1% production rate.
Right. Well, yeah. even then, I'm not sure what the momentum spread is after that. Maybe it's fine. But yeah, the production rate is low no matter what you do. Am I supposed to be also looking at this cost?
Oh, no, I mean, they
Okay.
stayed under budget. I gave them a budget
Okay.
and cost, so that
Okay, so I don't need to.
you don't need
probe.
to.
Okay, alright, that sounds good. That's tough, guys. Non-starters are tough.
All right.
Okay.
Compositeness tracking.
I guess. This. Whoever's this is. Have fun with that.
Okay, so now we're gonna start talking about the detector for the compositeness group, and this is the tracking detector. So to construct it, we use silicon cylinders starting at the beam pipe with radius of 1.1 centimeters in length, 0.02 centimeters, which was around the beam pipe, and each cylinder has end cap silicon disc on each side. So after having the first one, we added cylinders that were 4 centimeters away, and that was the distance is there to keep it cool. So first we started with 14 pixel detectors in the silicon, which had a resolution of 10 to the 8th and thickness of 0.05. And then after that we had 27 double-sided strips, so the strips go in different directions, so we can track in 3 dimensions, and that had a resolution of 12,000 and the same thickness as before. And then we had 11 single-sided strips with alternating strip directions for 3-dimensional tracking with the resolution of 12,000 and a thickness of 0.03 centimeters. And then after that, we had our solenoid on the outside of that, which was 1.3 meters thick. So the total radius of this detector part is 3.431 meters. We kept this detector relatively small sized so that the outer detectors would have lower volume, so they would be able to be thicker and have higher quality materials. So we diverted most of the money for this part to having high quality pixel detectors so that our multiplicity would be high towards the center where the particles are bunched up, and towards the outside we could have lower resolution detectors because the particles would be more out there. And we had a big solenoid so we could have a 13 Tesla magnet to detect how sensitive.
Explain to me resolution, because those are not units that I
Oh
understand.
yeah, so there's 10 to the 8th like channels in the
Oh.
Yeah.
Okay.
per
So
meter.
that's not
per meter
resolution,
squared.
that is channel count.
Oh yeah, like per meter squared, and then this is per 12,000 per meter.
And 12,000 per. So
Strips per meter of the.
what's 14, 27, and 11? What does amount mean?
Like that's just the number of layers of like how
So you
many.
have 14 layers of pixels.
Yeah.
And you have 10 to the 8th channel count out of all 14 or per layer?
Per layer. So. Wait.
What?
Yeah.
Wait. 10 to the 8th channel counts.
Or no,
So
per
it's
meter
14.
squared. Per meter
Okay.
squared of layers. So it's not 10 to the 8th per layer. It's per
It's
meter
not.
squared.
It's per meter squared.
Yeah. So there will be a lot fewer things. Oh, it doesn't say that.
It doesn't. Okay, wait. So how thick is all of the silicon combined? So like I started from the beam pipe and went to the solenoid. How
Yeah.
thick is that?
So that'll be 2.131.
2. Okay, because it's 1.3 minus or
Yeah.
4.3 minus. That's a lot of silicon. And how are you going to? I'm sorry. Are you done with the tracking?
There's one more.
There's one more. Okay, let's go to the next slide for the tracker, and then I'll come back and ask more trackers questions.
Is this composite?
Yeah.
So to calculate the sensitivity of our tracking detector to determine its effectiveness, we wanted to calculate the maximum measurable momentum of a particle in the tracking detector, which is given by this equation: P equals QRV times the speed of light, where Q is the charge of the particle, R is the circular path radius that a particle takes. So when it leaves the beam pipe, it travels on a curve because of the magnetic attraction of the solenoid, and B is the strength of the magnetic field of the solenoid. So for those values, Q, the charge of the particle, is standard for protons and opposite for electrons, which is around 1.602 times 10 to the negative 19 in coulombs. R, the B value, strength of the magnetic field. It was hard to determine like the average because we used several different materials, so we just used the 1/12,000 value for the channel radius, which was the value for double-sided silicon strips, and then obviously speed of light in meters per second squared. To calculate the circular path radius, we had to use this diagram over here, where D is the shortest distance from the center of the beam pipe to the outer layer of silicon, which I believe was around 2.091. So that's right before the solenoid starts. And then you solve that out to find R using this equation. So we plug in D and we plug in S, which is the channel radius I mentioned earlier. And using that, we could find the R value in meters, which is, not in meters, that's the wrong unit, but 6558.42. Oh, sorry, that is the right unit, right? Yeah, so that's this radius when the particle travels along this path. So 6,558 meters. And we plug that into the momentum equation, which would yield a very small number of joules. But when we converted that to TeV, we get around 25.5602 TeV as the maximum measurable momentum.
So you picked your detector. Sorry, are you done with the tracker?
Yeah.
So you picked the tracker and then decided how high of a momentum you could find with it?
No. So actually, I created a program that measures our momentum. So when we put in different values, we saw what the momentum would be for using various costs and types of trackers.
What other trackers did you look at?
No, like we tried to balance the amount of like pixels versus silicon and stuff like that.
Did you look at other types of trackers?
No, we used the material, like the types of materials that we were given.
So you're only given a certain type of material?
They could have asked for more, but there were sort of the standards were just
So
silicon.
like there's gas or silicon?
Yes, yeah, it's like they could use multi-wire drift tubes. They had those. The fancier stuff they would have had to research themselves. But
So you picked silicon
Yeah.
over the gas tape?
Yes.
Why?
But because we had like a lot of money.
So you went with the silicon?
Yeah.
Okay, so when I say resolution, I'm talking about how well within your detector do you need to be able to find a particle. Are you familiar with
Yeah.
that? So that means that I need a position resolution of like 8 microns.
Oh. Wait. Like.
So, is this okay if I?
you could talk about it. We didn't really.
Okay, so
Go through it in detail.
let's say that your particle went through, 3 pixels,
Yeah.
right? But nothing's perfect, right? In a perfect world, you'd be able to tell exactly, where it went, or even within that pixel where it went, right? But resolution is the real world, which way detectors work, right? So that means that you're going to be able to tell within maybe 1 or 2 pixels, for example, or something like that, how well your particle went through. So I was just curious if you know what your resolution should be. How well do you want to know this information?
Yeah, we couldn't calculate the exact distance like you were mentioning, but we tried to use more expensive and higher resolution materials like the pixels,
Mm-hmm.
because we knew that would give us a higher resolution, but we couldn't calculate the number
10 to
specifically.
the 8 was the max resolution for the
That's
pixel.
the max number of channels.
Yeah, or per meter squared.
Right. So that's a little different than the resolution.
Okay.
So like you're right, because the more channels you can put in there, then yeah, you can see if this one lit up versus this one. So there's probably a way we can translate your 10 to the 8
Yeah.
to this like micron thing that I'm looking for. what about readout? How are you going to read these guys out?
I'll intervene. I didn't make them do that part.
Oh, okay.
I let them leave that part out. Yeah, it's going to be rough.
Yeah. Okay. That's okay. So, but the goal was to make sure you did you get one budget for the tracker and the calorimeter?
Yeah.
And the and the muon. So you went with silicon because you had enough money to, but you also spent more money on your calorimeter.
Yeah.
So you're more. So what do you use the tracker for? What's the tracker used for in general?
Detecting momentum of charge.
So it's direction, which way it went, and detecting what type of particle. So did you guys as a group make the decision that the calorimeter was going to be more important because you're more interested in the energies?
It was like split up,
Okay.
almost half.
Okay. So you're right because right at D0 we spent more money on our calorimeter than we did on our tracker because we were more interested in the physics we can do with our calorimeter.
Yeah.
So you guys didn't necessarily make that decision, right? Okay.
Yeah.
Okay, that sounds good. Okay, I think I'd like to see calorimeter now.
Mandy, we're gonna have to go a little bit faster. We have like 20 minutes left, which is
Oh,
okay.
sorry,
For
okay.
10, it's okay. It'll go a little faster, I think.
Got it, go ahead.
Go ahead.
So here's our calorimeter for the compositeness group. So our EM calorimeter is on the top image, and we used lead tungstate scintillator and depleted uranium. And usually when you use lead tungstate scintillator, it's a homogeneous calorimeter. But because we were catching such high energy particles, we didn't have the money to just have a pure homogeneous calorimeter made of just pure lead tungstate. So we used the lead tungstate as just a really short radiation length material and also a scintillator. And we also included depleted uranium in order to make it a compensating calorimeter for the EM. And we had 10 total layers with 3 centimeters of lead tungstate followed by 1 centimeter of depleted uranium. And that was repeated 5 times. And that came out to a total of 33.5 radiation lengths. And for our hadron calorimeter, that's the second image, with the orange and purple. And it has, we made it out of tungsten and plastic scintillator. And we chose to use tungsten because it was pretty cheap relative to depleted uranium at only $800,000 per cubic meter. And it had a really short interaction length at 9.946 centimeters. And it was our hadron calorimeter was a total of 108 layers, 5 centimeters of tungsten followed by 7.9 centimeters of plastic, repeated 54 times. And that came out to a total of 32.4 interaction lengths. And we included caps because the tracking detector also included caps, and we were able to catch jets and elastic collisions. And the calorimeter has a total of 10 ADA segmentations and came out to a total cost of $3.123 billion.
Do you want to calorimeter?
You have one more.
Yeah.
Okay,
There's
go
one
ahead.
So the goal of our calorimeter was to detect the energy of the particles that went through it as accurately as possible. And so to do this, we set a goal in the design of our calorimeter. We wanted at least 99% of the energy of the particles to be deposited into our calorimeter in order to get an accurate measurement of the energy. And to do this, to test our design, we basically calculated the energy deposited for 2 particles. We did it for the electrons in the EM calorimeter and for the protons in the hadron. And these particles both had an initial energy of 12 TeV because that was determined as reasonably the highest energy particle based on the accelerator. And so to do this, we used the following equation over there. We gave the fraction of the energy deposited by the particle. That's determined by the number of radiation or interaction lengths of the layer and the critical energy of the material. And the critical energies and the radiation and interaction lengths of the materials we used are given in the table right here. And so, however, once we calculated this, it was a little more complicated because we had a sampling calorimeter. So because of the alternating layers, we had to calculate it recursively. So we basically summed up the energy deposited in each layer to get the total energy deposited, and we found out that for electrons, in the EM calorimeter, 99.4% of its energy is deposited, and for the protons in the hadron calorimeter, 99.1% of its energy is deposited. However, for protons, the 99.1% being deposited is just in the hadron. If you include the EM as well, the interaction rates of the EM, 99.4% of its energy is deposited. So, because we achieved the goal that we were given of 99, at least over 99% of the energy being deposited, our calorimeter is able to track the energy well.
And then is there a muon detector for the?
Yep.
Alright, so let's see that and then I'll ask more questions.
That's good.
I will have calorimeter questions, guys, so when we're done with the muon.
Okay, cool. So, compared to our last two detectors, the muon detector is pretty simple, or I guess as simple as physics gets. So, we have 8 layers of silicon right around the center, and then we have drift tubes, or I guess drift chambers, and resistive plate chambers that kind of cap like the barrel region, which is like where the muon detector is like over the other tracking detectors. The outer radius is quite large with 132.14 meters, and the inner radius is 100.8.63 meters, making it pretty large. It has 1.3 meters worth of toroids, and it has 4 toroids. Each toroid has a strength of 13 Tesla. It has 125 total drift tubes, I guess, or 270 cathode strip chambers, and 305 resistive plate chambers. It's solenoid or returnial. Its efficiency compensates for the low collision multiplicity that happens, which, yeah, so because it's 13 Tesla. So it's pretty simple. Also, it comes out to be about 583 million. So, yeah.
Yes.
Okay.
Okay, so this is the same equation that was used for the tracking detector. So we need to measure the sensitivity of this detector, as in like the highest energy particles that it can actually detect. So we do that with the sagitta, which is a measurement of how far away 2 chambers need to be in order to detect a particle close to them. So the calculations here are done with assuming the energy is like 1.8 times e to the -6, with the radius of curvature as about 9 times 10 to the third. However, this energy value is very small, and given the cathode strip chambers in our budget on the muon detector, we can't get to a sensitivity that low. So we basically kind of reverse engineered what kind of energy we can detect, and we got that it was about 2.239 TeV, because we use cathode strip chambers which have a density of 1/300, and so a sensitivity ultimately came, a sensitivity value came out to 3 times 10 to the -2.
Okay. The muon detector, that looks pretty reasonable. Makes sense to do something very simple, right?
Yeah.
Because the whole point is that if you're out there that far, then you're muons. So that's really all that matters. For the calorimeter, I sort of feel like your EM and your hadronic calorimeter are backwards. Because it seems, I mean, uranium is very thick and dense, right? So don't you want that to be outside because you want lower material on the inside and more material on the outside?
Well, what we wanted to make the EM as small as possible, so that everything outside of the EM would also be have a lower volume. So with the EM, we used uranium because it had a really short radiation length, we thought that would, and it would make the EM shorter.
But wouldn't that also stop all of your hadrons as well? Right, the point of the EM and the hadron is you only want to stop EM, you only want to stop photons and electrons in that layer. You want everything else to go through. So, but if you have uranium in there, wouldn't that stop everything?
Theoretically, the particles are really, really high energy, so they should pass through it, but it
Okay.
would affect it. So it might stop
But
some.
then also, wouldn't you want the scintillator to be closer because the scintillator is going to see photons and electrons more so than, right?
Yeah, well, I think in the EM we had much more scintillator, and we did.
The EM you didn't have any scintillator.
We had lead.
Okay, the lead. Okay.
So we had, I think we had 3 centimeters of lead tungstate, and then just 1 meter of depleted uranium. So we had mostly lead tungstate scintillator in our EM.
Okay. I still think the uranium should suck up more hadrons than you want it to, but okay. Okay. Next.
I think maybe we'll do the next detector, just do all
Yep, let's
all
do
of them,
that.
and then
Sounds
do
good.
questions at the end. If you click again,
Okay.
that was your slide. Man.
Okay, yeah, I know that. Okay. So this is the detector design for the chameleon study that we're doing. So for this, we wanted, since we're just looking at the rate of the Higgs boson production, we want very high acceptance. So that went into the shape we designed. So what we decided to do is to start out around the collision point with a spherical layer of the of strips of silicon strips. So in the sphere here, it has a total of 80 strips of or layers of silicon sheets that are 0.0005 meters thin. They're each spaced 2 centimeters apart. The first 15 layers of this sphere are the pixel sheets, and then the next 65 are double-sided, and we figured that out just looking at our cost, what that came out to be. That's what worked out well for us. Then, because the reason we have a sphere around here is because as the particles that come out from the collision, as they come out, they'll pass very directly through these sheets if they come out here. But as they come out along the beam pipe, which for this experiment, we wanted to measure very precisely. So we have it pretty long. It's 5 meters long. So each of these silicon layers are staggered as it goes along the sphere, so they match up, but then they're staggered. So the ones in the middle are shorter than the ones on the end. And those, they follow the same thing there. Or no, but the cylinder are all double-sided sheets. So the reason we have the cylinder outside of the sphere is so that as it's traveling along the cylinder, it'll be traveling through more empty space, because it's if it's going like this, it'll be traveling for longer through the empty space. So we want it to go for longer, so that it can reach us, so it can be tracked as effectively as in just the sphere, where it's traveling through these sheets more directly. And our cost came out to be $2.902 billion.
So the sensitivity of our detector, there's a model of how we calculate the Sujita. The circle shown out there is the detector, and we got the Sujita that we wanted by first starting with a momentum that we wanted to find, a goal momentum, and we wanted around 11.777-ish, almost 11.8 TeV per C momentum particles to be found, because the accelerator produced collisions at an energy of about 35, and we figured about 1/3 of that would be a reasonable energy to search for particles at. So we took the momentum and we plugged it into the equations at the bottom here, and we got the Sujita that was required for that, and we took that Sujita and we rounded up and we got 9,864 channels per meter for double-sided silicon strips and 94 million-ish for our silicon pixel channels per meter squared.
How do you pronounce that?
Virginia?
Is it just that?
Yeah.
Okay.
That's fair.
For our EM calorimeter, we decided we wanted to have a homogeneous calorimeter so we can better track the energy resolution throughout the path of the particle. And so we decided to use lead tungstate scintillator for that purpose. And we had 3 layers and 3 pairs of end caps, all 0.114 meters thickness. And we decided to split up the lead tungstate into layers so that we can better track particle showers. Our segmentation is 60/30 P-eta segmentation, and our photodetector type is APE for high sensitivity because we can afford it. The radiation length parallel to the beam pipe and perpendicular is 38.1, and we chose this amount so that we could measure the particles that have 11.87 TeV. And we decided to put the solenoid outside the EM calorimeter so that we can minimize the volume of the EM calorimeter and minimize different costs.
Well, I'd like to mention that on the tracking detector, we do have disc end caps, and those are double-sided sheets.
Okay, so directly outside of our solenoid, which is 0.34 meters thick, we had our hadron calorimeter, and the total cost of our hadron calorimeter was $2.464 billion. And it was composed of 49 alternating cylinders of plastic scintillator and depleted uranium absorbers. And for the end caps, we used 39 alternating layers for each of the end caps. And we decided to make a compensating calorimeter using depleted uranium absorbers because as hadrons pass through the uranium, it releases energy through fission, which helps lead to higher energy resolution, which makes our calorimeter a lot more sensitive. And we also used in our cylinders avalanche photodiodes, which are very sensitive, to convert the energy released by the scintillators into electricity, and that helped give us more sensitivity. And for our cylinders, our Phi-eta segmentation starts at around 2010 for the innermost layers, and it increases to about 60/30 for the outermost layers of our hadron calorimeter. And there's 34.4 interaction lengths perpendicular to the beam pipe for our hadron calorimeter. And then for the end caps, we used MAPMTs, which are multi-anode photomultiplier tubes, and our Phi-eta segmentation increased from 2010 to 50/25 from the innermost to outermost layers. And we also had 28.9 interaction lengths parallel to the beam pipe in our hadron calorimeter. That's not including the EM calorimeter on the inside. So the maximum energy that we're able to detect for a proton, which is to say the maximum energy a proton can have while still being stopped by our calorimeter, is 11.78 TeV if it goes perpendicular to the beam pipe, and if it goes parallel to the beam pipe, or if it goes, then it's 0.3 TeV. And if you notice, this number is kind of small, but also in our muon detector, we have a layer of iron absorber, which is the return yoke, which also helps to ensure that all particles, or all hadrons get stopped before reaching outside.
Okay, so this is the design for our muon detector. So our overall cost was $1.281 billion. So like Josh said, the first part of our muon detector was a 1.3 meter thick iron return yoke. So like Josh said, it does act to stop any stray hadrons that may not have been stopped within the hadron calorimeter, but it also acts to contain the magnetic field from the solenoid. So in our cylindrical section, our cathode strip chamber layers have 0.1 centimeter thickness. Our drift chamber layers have 2 centimeter thickness, and then all the layers are spaced out by 2 centimeters. So this is like the pattern we used for our layers. And the reason we did this is because CSC, or cathode strip chambers, have a much higher channel density than drift chambers. So we put them in the beginning, middle, and end of the cylindrical section. So we have the best possible like resolution image of like the muon's path through the detector, and also helps in our sensitivity. And our end caps are also very similar in terms of thickness, but the spacing is half of that of the cylindrical section, and the pattern is also pretty similar, and it has the same reasoning. So we had 24 toroids around the cylindrical section with a field strength of 6 Tesla, and we had 6 toroids around each end cap, and they had a field strength of 4 Tesla. And the overall dimensions was a diameter of 29.2 meters, and this should be length of 28.4 meters.
So I was in charge of the sensitivity analysis for the muon detector. So here we have an up close look. These are the CSC, the purple parts, and then the blue parts are the drift chambers. And so we strategically placed the CSC in the middle so that we could get a good measurement of the cicada. And so CSC has 300 wires per chamber per meter. And if you want that in resolution, it's 3,300 some microns. And so our cicada ended up being 1/300. That's the maximum we could, that's the smallest we could detect. And so using this equation, as a cicada, Q is the charge of the muon, V is the magnetic field, which for the cylindrical part was 6T, and then we had the path length for L. We calculated our momentum, or our max sensitivity, for the cylindrical part, the barrel part. We calculated 1.07925 TeV/C, and for the end caps, we calculated 0.1797 TeV/C. And while the end cap number is pretty low, it does what is intended. It detects for muons, and if it's necessary to, you can always trace back the path of the muon. So you can see the path. So it gives the path of the muon in our detector, and you can always trace that back to the first tracking detector to find the actual momentum of the muon. So this is just to identify the muons.
So I missed it on the hadron calorimeter. Is that inside the?
That's outside the
That is
solid.
outside. Okay. So how well do APDs work in magnetic fields for the EM calorimeter? Did you check that?
I looked it up and it said they were safe.
They were good in magnetic fields. Okay, that's good. So this is looking for the chameleons.
Yeah, the rate of the fuse plasma production.
So rate of the boson production. So what, in your opinion, what's the most important detector in this?
Probably tracking.
Body tracking. I agree. I just don't agree.
Yeah, we spent the most money on the tracking detector, which is $2.9 billion.
Can you go back to the tracker one more time?
Sure.
I don't. Okay. What do you mean by sheets of silicon?
So it's like the
Layers.
yeah. So
It's just like you're gonna get a bunch of silicon wafers, kind of a thing, and
so
you're gonna.
they're the layers that are around, like it's similar to the ones you had it before, like they're layered pieces. So like
There's strips.
well,
Yeah, so-
well there's the pixel and the double sided. So there's the
Yeah.
different types. To my understanding, our group's understanding, this is like pretty standard.
No, I just haven't heard sheets.
Oh.
Right? You
Oh,
hear
it's just-
you hear
it's
strips
just-
or
it's
you
just
hear
like
a layer made of strips. So
fine.
Oh, okay.
Dr. John
Okay,
is a program
fine.
that
Okay,
will
all right, that sounds good. Okay. All right, I think I'm good.
Okay. All right. You guys all did a great job. Sean has a question. Sean, you can ask your question later. We're trying to time. So, the only so now we do have to go soon, but if you have general concepts, and then the idea is, so they did build the accelerator with 2 collision points, but imagine DOE cut the funding and you can only fund one.
Yeah.
So if you can only fund one detector, which one would you choose? That's the
Oh, it's a big moment. It's a big moment.
Big moment. Goodness, you guys. Okay, so
This is real.
We already won.
So I have to say that although I see issues with both detectors, for the most part, since the goal of the first detector is to do the compositeness, and that depends on the die-jet mass, and the calorimeters are very important. And I don't believe your calorimeter plan. So I think that the second one would be the one I would fund because I think it's going to have a higher chance of doing what it's supposed to do.
All right. Okay, we have to get going. Can we please thank our scientists again?